This is Unit 3, Lesson 4 in Algebra 2. It's called Linear Programming. And in linear programming, what they're going to give you are a bunch of inequalities, and they're going to make you graph those inequalities. And what's going to happen is as you graph the inequalities, you're going to end up with a shaded region within that graph. We're going to actually do the graphing on Desmos. We could do it by hand, but if we do it by hand, we have to get all these different equations in slope-intercept form and then graph them, and it just makes it a lot of work and it's very time-consuming. So what we're going to do is we're going to take these inequalities and we're going to graph those in Desmos. Now, what you need to know, the inequalities in a linear programming problem are called constraints. So we will take the constraints and we will graph them in Desmos, and then what's going to happen, and I'm just going to do a real rough sketch, we'll end up with something like this. Okay, it's shaded that way, this one's shaded that way, this one will be shaded this way, and this one will be shaded that way. And what we end up with is we have a region that is shaded, and that region is a polygon of some sort. Okay, now it doesn't have to be an enclosed shape, but what we're looking for is the vertice points where we have the shaded region for all four of those constraints. And so if you see here, we've got a shaded region on the inside in the middle, and what we're going to take out of that are these vertice points. Okay, so that's what you're going to do in Desmos. I want you to take these four inequalities, put them in Desmos, graph them, and then put your cursor on each of the vertices where the shaded region lies and write down those vertice points, okay? We will use this equation with those vertices later. This equation is called your objective equation, and we will use the vertices and plug them into the objective equation to either find a maximum or a minimum value for your vertices. That's what we're basically finding when we're doing linear programming. Okay, so go to Desmos, graph these, pull out the vertices you get, and then we'll come back and we'll finish the problem. So I've gone ahead and graphed these in Desmos, and you can see the constraints here that I put in. Notice I did not have to change those to slope-intercept form or anything. I just put them directly in just like they were listed on my paper. And then I've got them graphed over here, and yours may be in a different color than mine are. That's just generated randomly in Desmos. There's nothing that I've done here to generate these specific colors. And then what we're going to do is we're looking for the polygon or the enclosed region, and we're looking for the vertices of that polygon. In this case, you see here, it looks kind of like a parallelogram. I don't know if it is or not. It could be. But you see this quadrilateral here. And what I'm going to do is I'm just going to click on the ordered pairs where they are, and I'm going to jot down those ordered pairs. So one of the intersection points or the vertices is 0, 3. So I'm going to write that down. The next one is 3, 4. Then I don't have another one until I get right here. That's at 6, negative 2. And then the last one to form that region is 3, negative 3. So I have all of those ordered pairs. I've written them down. And now I'm going to take those ordered pairs back to a piece of paper, and I'm going to finish the problem using the objective equation. All right, so back to my original problem. I have graphed the constraints and I came up with the vertices. So I've written down my vertices that I took from Desmos. They're not in any particular order. It really doesn't matter what order you put them in. And I'm going to use those vertices and I'm going to plug them in to my objective equation to get a number. Okay, so for this one, if my first vertice is 0, 3, I'm going to plug 0 in for x and 3 in for y. So if I do that, 0 in for x gives me 0, 3 in for y gives me 12. So if I add those together, I get 12. If I plug 3, negative 3 into the objective equation, 5 times 3 is 15. 4 times negative 3 is negative 12, giving me a 3. When I plug in 3, 4, 5 times 3 is 15. 4 times 4 is 16, which gives me a 31. And then 5 times 6 is 30. And 4 times negative 2 is negative 8, which gives me a 22. And with these linear programming problems, they're going to ask you to find either the maximum or the minimum, or they may ask you to find both of those. The maximum will be the largest number you get for those four numbers. The minimum will be the smallest one. It is okay, sometimes they might be negative numbers, that's not a big deal. But for this one, the maximum here is 31, and the minimum is 3. So I've answered that linear programming question. Here is another linear programming example. The objective equation is f of xy equals 2x plus 3y. You have three constraints in this problem. Negative x plus 2y is less than or equal to 2, x minus 2y is less than or equal to 4, and x plus y is greater than or equal to negative 2. And then I want you to find the vertices, and I want you to find the maximum and the minimum. So go ahead and copy this down, put it in Desmos, see if you can finish the problem, and then we'll compare our answers. I have these graphed in Desmos. If you look here at the shaded region, you've got a shaded region here that appears to go on forever. We only have three equations, and it looks like we've got two lines here that look to be parallel, and then a third line that cuts through those two, and the shaded region where all three are shaded is this region right in here. So that's not an enclosed polygon of any sort, it's a shaded region that does go on forever. So when you have this situation, you're really doing the same thing, you just have less vertice points. If you look at this, the vertice points are the 2 points that connect this line, and this line to form that region. So I only have 2 here. I have negative 2, 0, and 0, negative 2. Okay, so those are the two ordered pairs that you're going to plug in. And when you do that, one of them will be the minimum and one of them will be the maximum. So when we did Desmos, we found that the two ordered pairs, or the two vertex points, are 0, negative 2, and negative 2, 0. So I'm going to plug those into my objective equation. So if I plug 0, negative 2 in, 2 times 0 is 0, 3 times negative 2 is negative 6, so that gives me a negative 6. And when I plug negative 2, 0 in, 2 times negative 2 is negative 4, 3 times 0 is 0, so that gives me a negative 4. So here my maximum is negative 4 and my minimum is negative 6.